You on our merry way today. So the next topic or next presentation up for man, this is long. The next talk is going to be Patrick Matlock, and he's going to be presenting his paper titled "The End of Digital Neuroscience: Kolmogorov Complexity, Spiking Neurons, and the Rise of Brain Organoids." Okay.
Hello, everyone. Thanks for coming. I'll try and speak up so people can hear. I didn't mean to be super pretentious, but I put my background on the slide. I have a deep technical background, and what I really do is cybersecurity. So this long-winded thesis statement from my paper, what it really means is that I was interested in the neural networks that are in silicon, and I had been thinking about how that pertains to the neural networks that are in our brain, and I got interested in looking at human brain organoids. So I kind of compare and contrast all of that. So the beginning of how I built the paper, you can blame Dr. Ray who left, but Alan Turing, he's famous for the imitation game and Turing machines. And he proposed in 1951 paper on you have two entities having a conversation. They can't see each other and they only can communicate via text. And there's a judge, and the judge tries to decide if the person being queried is human. So we have a famous researcher in cognitive science at Waterloo, Chris Elias Smith. He wrote a paper kind of pertaining to addressing Turing's paper. He has a real brain. He's actually built in engineering at Waterloo. This is his book. This is his skinny book. He has another book on neural networks that's around, I don't know, 3 inches thick. The guy is he's out there. So anyways, Chris Elias Smith, what he thought about was you have two entities that do the same function, and does implementation matter? I also brought a prop. So Scientific American from February of this year talks about brain models, and he made the cut. So how fortuitous. They give a bunch of criteria to how they evaluate the models, but as I was talking to Dr. Hayden, it's not very good. In Chris Elias Smith's case, the quadrant, he does the semantic pointer. The piece that he's missing was clinical use of his model. So I'm not really sure that how they evaluate these things is actually maybe the way that should have been done. So in Turing's paper, he looked at things, the concept is called functionalism, and he used a top-down approach. So prior knowledge, concept-driven. In Dr. Ray's class, we had a different person credited with functionalism, but my research showed Hilary Putnam and Jerry Fodder. So this is the paper that Chris Elias Smith did. And what he did is he used a thing called Kolmogorov complexity theory to kind of compare two implementations of functionalism and then kind of make an argument. Kolmogorov complexity theory, the reason I know about it is I worked for a long time at the University of Waterloo, and I actually worked in computer science for a while, and they had an expert, Dr. Ming Lee, and that was his expertise, and so I knew about the topic. So this was Elias Smith's argument. You have two entities, and they have to decide friend or foe fast enough so they both live. One takes 10 minutes to compute that. The other takes 10 milliseconds. Another concept here from Turing is that our brain, human brain organoid, and all of your computers, those are computers. So you can apply asking this to our brain. So implementation matters. And that was the argument that Dr. Elias Smith mentioned. So here's Kolmogorov, and notice at the end he's famous for this Kolmogorov complexity theory. What this algorithm really says is you have two computer programs. So remember, our brains are a computer, human brain organoid is a computer, and your computers are computers. Which one can compute and output basically the most efficient way? I show this slide. This is from his book because I wanted people this morning were talking about bias. So in the red box are the molecules that get transmitted back and forth between the neurons in our head and in a human brain organoid. And just intuitively, you can see that the same action can happen over and over again. The number of molecules going back and forth will never probably be the same. So there's a variance and a bias in how the data is transmitted. The green box shows when you have some stimuli traveling down the neuron, you get these spikes that represent potential. This picture is good because it shows the spikes as discrete lines, and that'll come into play later. This slide is also from his book. It shows the path of information going down a nerve. The reason why I wanted to enter it is because the neurons in your head, two neurons that do exactly the same function, are never the same length. And some of the neurons in our head are up to 15 meters long. So what that means is that there's like a little bit of a phase shift. It isn't the same homogeneous type of transmission that would happen on like a silicone digital device. So I started thinking, what else has properties like the human brain? Because I was interested in, is there anything else that can maybe address the friend or foe problem? So I had been looking into human brain organoids, and I'm like, whoops. And I'm like, well, that is made from the same material as our brain. Can these things be used as a computer? So I researched them. I found that they actually have all of the same, you can buy them. They have the same properties as our brain, all of the structures. Then I said I wanted to eliminate some of the bias like they were talking about this morning. So our brain, a human brain organoid, and the computers that you use, the type of machine they are is a linear bounded automata. So meaning like when I'm comparing the human brain organoid, our brain, and a computer, I'm talking about something in the same class of machine. As far as languages, all three, human brain organoid, our computers, they all have a context-sensitive grammar. So in that particular, with those properties, they're equivalent. So to review, human brain organoid, silicon computer, linear bounded automata. They all, by the definition of being a linear bounded automata, they persist data. They all can take and give out data, sensory data. They all have a type of neural network inside. They all have a logic system. So from Turing's functionalism, they all match up. But then I wanted to think about the problem in a different way. So I didn't totally pull the Kobayashi-Maru, but I did flip the problem around. And I said, okay, so functionally, human brain organoid, brain, silicon computer, they're functionally the same and they look like they're doing the same thing top down. What about from bottom up? So even though it's cut off, they're data driven, the stimuli and the details matter when you're coming up from the bottom. So the devil's in the details. So we've made the assumption, I probably convinced you that they're all linear bound automata. They persist I/O. They all have a logic system. And like silicone, an HPO is not living tissue, which is important. But with a human brain organoid, I can run an MRI machine against 1,000 HPOs or 1,000 times against one HPO, and I can say where is the concept of a tomato? Where is the concept of a chair? What neurons fire? Give it logic problems. What neurons fire? So I can start building up empirical data. The last thing I'm going to look at is the biological neural network versus the silicon spike neural network. This is also from Chris Elias-Smith's book. I mentioned before that the action potential is going down a neuron. Have spikes. The top part of the picture, we can logically kind of envision those spikes collapsing into just one discrete spike. This particular slide, what I want to show is a failure, but I want you to look at the gray around the spike. That's actually a probability distribution, which means that it's not a single event. It's something that lives in a distribution. So, did you catch that? Human neural network, human brain organoid. The data is a curve, it's continuous data, where in the neural networks in silicone, those are discrete spikes. Oops. So everything in your computer, when you have a logic gate, the same function is built and deployed the same way. So the whole thing is homogeneous. Everything is the same. We're in a human neural network, the organic neural network and a human brain organoid. It's heterogeneous. The neurons are not the same size for the same task. Now, in a spike neural network, say like for generative AI, you have two neural networks kind of going against each other. Where in our brain, in a human brain organoid, there are many neural networks all interconnected. So you have two compared to n. Time on a computer is probably a crystal that times the computer. Everything is happening at discrete fixed time. In our brain, because of the different lengths in a human brain organoid, the same event, the same data can be showing up at different times. That little bit of difference also helps our brain. We have things that drive dopamine, serotonin, so fight or flight, make us feel good. There's no such property with a silicone or a spike neural network. I thought about this 2 days ago. We talk about Gen AI and ChatGPT and our friend Claude. They have like a window of how the token space of memory. So how much of what it knows it can look at once. The really good large language models, that window is 128,000 to 2 million. But in our brain, it's actually considered an infinite token space. So the amount of data that you have access to in your brain, in the human brain organoid, is much larger than the silicon network. I gave you the wrong slide. That's not actually the lymphatic system, it should be the limbic system. So the limbic system is emotion. So we talked before about some of the other presentations about using a chatbot as therapy. The chatbots have no emotional components, where our human brain and human brain organoid has a structure for the limbic system, so there can be an emotional component, could be wired on. Belief systems. So true opinion, true belief, justified true belief, knowledge. Where is that in our brain? Is it actually in our brain? If we could run an MRI machine against human brain organoid over time, play with it, experiment with it with concepts, we'd be able to see, because there are some theory of mind people that believe that the belief system is not physically in our brain. So the continuous property of the neural network in human brain organoid and our human brain is always greater than the discrete spike neural network. I talked about Kolmogorov, his theory early on. It's actually a subset of Shannon's information theory. So the same word in Vietnamese versus English is not as efficient as a Vietnamese language. So I'm using the opposite of Shannon's information theory. In this analogy, the Vietnamese represents our brain information and human brain organoid. And the data here represents the silicon computer. So what am I really saying? The natural numbers are, you can think of as the counting of the spikes in a silicon neural network. The real numbers represent all of the information in the human brain neural network and the HBO. So to go back again, this big number here represents continuous data, and the Vietnamese represents spike or silicon neural network information. You can see that visually, conceptually, this is much larger. So some counter arguments. A year ago, human brain organoids were very tiny. Okay, they're too small. Those human brain organoids they would have 10 million neurons, where our brain has 80 billion. Somebody figured out if you grow them in an oxygen-rich environment, they will grow. Then there was the problem of, at a certain, when you started growing them, the human brain organoid would start to disorganize. So a Japanese researcher figured out some type of specialized gum that caused the disorganization to stop. So the human brain organoids could start being grown bigger. Scale, in other words, like acquiring it and maybe building a network of human brain organoids. Dozens of companies sell these things now. In Canada, you spend $1,000 US, you get a development kit, and you get a human brain organoid, a bunch of them, and you get the medium to grow. Development kits are like single board computers, like a Raspberry Pi, Rabbit microprocessor. And there's actually like a little contraption you can put over a human brain organoid when it gets to a certain size, and you actually can program it and do input output. So here's a graph from one of the research papers in my paper, where it shows that when the oxygen was added, how much bigger the human brain organoid grew to. Here's the company I used in my paper. I put this slide up because you can buy a male and female model. I don't know why. So ethics of AI, I put some ethical considerations. So Descartes talked about our mind. He was a different structure for him, but the concept is good. That it's human material extended in 3 space. Kant's categorical imperative. If the human brain organoids are not alive, then they can be treated as a means. If they become sentient, then they have to be treated as an end, just like us. In Kant's case, he was really talking about humans. And legally, it's not living tissue. So you can do whatever you want with it. Once again, humans have 80 billion neurons, and the HBOs, I want to say they're in the multi-billions now. I want to say 40 to 50 billion neurons you can grow them to. We talked, the previous talk, about the sensory system. MIT professor analyzed the hand. There's 17,000 sensors in the hand, and we can't build that today. So the input coming in on some of our sensory systems, like synthetic systems, to go into a synthetic brain, even a human brain organoid, we're not even close. Wrong slide. Limbic system versus silicon DNA, there's no equivalent. So yeah, in our brain, the limbic system does fight or flight, and it pulses the old brain. Belief system, as I talked about, where is it? We can't really know right now, but if we could run an MRI machine against 1,000 experiments on one human brain organoid or 1,000 across the board, we'd be able to get some empirical data. In the continuous data that's in our brain, in the neural network, human brain organoid is always greater than the discrete spikes that are in the silicon systems. Okay, so I'll just go through this really quick. Disembodied mind, sentient, probably get there. Legally, could be despots. Personhood, right now it's illegal for these things to even be considered a person because they're not born of a woman. That's actually in Ontario law. We talk about ethics of environmental. These things have very low power. The human brain is only 25 watts, where like ChatGPT is 2,500 gigawatts. Conclusion, human neural network, the HBO neural network will always be superior to the silicon version. They're not living, so you can experiment on them. Thank you. Questions? Just like that.
What do you see as the most salient?
That's a loaded question. I don't think that I consider. So I've done research. I've built large language models. I've used Llama 2, Llama 3 for my cybersecurity work. I consider the large language models just to be a corpus of tending towards a little bit of knowledge and a bunch of true belief. So I don't consider it anything more than that. So it's a corpus, but also you think about how they were trained. They were trained, they were scraped all of the data on the internet, books, papers, whatever. So if you have A and not A, you can prove anything is true. So I think we're working towards eliminating not A. But I think your talk, Dr. Marino, some other people with data and trust, I think we need to go back to the beginning, and I think we need to classify all of the data: true opinion, true belief, justified true belief, and knowledge. Let's face it, knowledge gets disproved all the time. So if you go back to the beginning, you have a classification for every type of piece of data. As time goes on, you reclassify the data up and down that tree. That will actually help with trustable AI, which I've also looked into, and explainable AI. Did I answer your question? Anyone else? I know about it. There are, when you say neomorphic, you actually mean biological material on a chip? So I haven't deep dived them, but we talked about buffer overflow, and the GPUs have they're all fixed. The gear inside is all fixed size, where our brains account for things with different lengths. So there's error correction that way. And I think until you get to a model that's like that, which human brain organoids are, I think you're going to run into the same problem. I now, like, we go back to this again. Every one of these models is based on silicone, but I just showed you a material, a wheel that we don't have to build. We just have to pump it up. We have to be able to, we have engineering problems to overcome that has all of the wedges of the pie already built in. And we can use the data that comes out of the human brain organoids as training data for all the silicone-based things, because we'll be able to catch all the boundary cases. So that's what I think. I think that should be maybe abandoned. Bills?
I guess you talk about like having limbic capabilities for some of these. I guess I'm curious about what like an emotion means in a disembodied state, because I understand that you guys can think it's not conscious.
Yeah.
So I don't know if that relates.
Here's my
yeah.
Would you hire a therapist that was a sociopath? Because by the definition of a sociopath, they have no emotive properties. So I have friends. What's that? Oh yeah. Well, I think you find out probably. But the point is that you're without the ability to have any kind of emotive properties. I don't know if they can totally relate to us. But just being able to have that wiring in place opens up. Then you can say, yeah, we got an apple and an apple. Well, right now we have an apple and we got nothing. So that's that. Did that answer what you're?
Yeah, and you're getting closer. I guess my other thing is kind of like a question, like, what is like? So say you're able to build an organized neural network, whatever. What does maintenance look like on that? Like, is it different than how different is it?
Well, I just have a couple now. But I know, like UCLA,
yeah.
The sixth floor of Engineering 7 at Waterloo, the front half of that building is kind of controlled by this guy. It's all silicone based, the neuroscience wing. They have a whole floor at a gigantic building at UCLA that's dedicated to human brain organoids. It's kind of exploded in the last maybe 14 months. And I think for cognition, I think because of the things that I said, running the MRI against it 24/7, it's currently not living tissue, you can kind of constrain it so it's not quite the same on neurons that we have. I'm going down that path, but I'm a cybersecurity guy. But I'm going down that path because I think that it might be, it might be something. And it's like this pink goop is what they live in. My wife says it's creepy. It is creepy, but eventually maybe it won't be creepy, right? So, yeah.
My question is, do the human brain organoids suffer from the same pitfalls of the running recursive loops can get very tiring for neurons or exposed to a certain type of stimuli very continuous very long time with like essentially degrade the ability
Yes.
to get.
Yeah, that's actually one of the,
Is there a way to like check that for algorithms?
well, I think like right now, like I said, the programming for these things is like what I have is very, it's very simplistic, right? But I think it's an engineering problem. And I think eventually, the other thing is they don't look like, the smooth, they look like Goku from Dragon Ball Z. They're like spiky, like they're not curved. It's like they're like creepy looking. I read, I was like, why is that? And I learned that our brain cavity forces the brain to, and that geometry actually means something. Yeah, so I'm like, so then I predict and think, okay, got to put pinky inside of a brain cavity to make it, got to make skull. So yeah. So anyways, yeah. I look at it this way is that you don't know until you know, and by running, running experiments, like statistically meaningful experiments, where is the chair? What neurons fire in the brain? You can take that data and you could use it against the silicon systems to improve all the boundary cases, right? And you can take the things like, because it's got a little bit of the limbic system, you can see, hey, I'm going to cause this thing a lot of pain, and I'm going to see what neurons fire. What does that do against the silicon system, right? And like the previous person, her talk, that's why I brought up the thing about the sensory systems, because if I was a young researcher and I was going into something, there's a huge divide between the AI systems and the sensory systems. They're not, we're like probably 40 years behind. And I think that once that closes, I don't think we can reach SAGI, any of that, until that closes. But once it does, we're just going to be like Wally. That's what I think. Yep.